Welcome to InfiniteGyan. At InfiniteGyan, we help you learn, understand, and grow. Every lesson is a step towards endless opportunities. Join InfiniteGyan and let's explore knowledge without limits.
Hey there, and welcome. You've probably seen the number line before, right? Just the straight line that stretches out forever in both directions. But what if we thought of it as a whole world, a place with its own unique inhabitants? Well, today, that's exactly what we're going to do. We're going on an expedition to explore this world and meet every single number that lives there.
So, here's our mission. We're going to walk this line from end to end and collect every number we find. I want you to imagine you have a bag with you, and we're going to try and capture them all. This is a journey of discovery to find out who or what actually lives on this line. And that's the big question, isn't it? As we're walking along, what kinds of numbers are we going to find? Are they all the same, or are there, different tribes, different families of numbers living here? Let's start our walk and see what we can find.
All right, first things first, we're going to start by picking up the numbers we all know and love, the ones we learn as kids. It's time to collect the counting numbers.
So, as we start walking away from the center in the positive direction, we immediately bump into 1, then 2, then 3, and on and on. These are the natural numbers, and we use the symbol N for them. They're really the foundation of our whole collection.
So let's take a peek inside our bag. What do we have? We've got 1, 2, 3. We keep walking and find 74, then 601, and this just keeps going forever. And just like that, our bag already has an infinite number of things in it. Pretty wild, huh? But believe me, we've only just begun.
But wait a minute, hang on. When we started walking forward, we stepped right over our starting point. Let's backtrack for just a second and pick up that super important number we missed, 0. Now, when we add 0 to our bag of natural numbers, we get a new collection. We call these the whole numbers, represented by W.
Okay, we've got the positive side covered, and we've got 0. But what about the other direction? If we look that way, we see a whole other infinite set of numbers stretching out. -1, -2, -3, and on. Let's just scoop all them into our bag. Now, this complete collection, the positive whole numbers, the negative whole numbers, and 0, that gives us the integers with the symbol Z.
Now you might be thinking, why Z for integers? Wouldn't I make more sense? And that is a great question. It's actually a little piece of math history. The Z comes from the German word zählen, which just means to count. So it's a little nod to the origins of these numbers.
Okay, so our bag has all the whole number stops along the line. But look at all that space in between those numbers. It seems like there's a lot of empty space. It's time to look a little closer and start filling in the fractions. These numbers living between the integers are called rational numbers. The name actually comes from the word ratio. Their symbol, Q, comes from another word, quotient. A number is rational if you can write it as a fraction, P over Q, where P and Q are both integers we've already collected.
But there's one really important rule here. Q, the number on the bottom of the fraction, can never be 0. Why is that? Well, think about what division even is. If I say 12 divided by 3, I'm asking, how many groups of 3 can I make from 12? The answer is 4, nice and easy. So if we tried to divide by 0, we'd be asking, how many groups of 0 can I make from 12? It just doesn't make sense. You could pull out empty groups forever and never get to 12. So in math, we just say it's undefined. We simply can't do it.
So here's the cool part. This new collection of rational numbers is our biggest one yet, because it includes everything we've already picked up. Any integer, like say -25, can be written as a fraction, right? Just write it as -25 over 1. So every single integer is also a rational number. Our bag is getting seriously heavy now.
And this shows just how packed the rational numbers are. Like, let's say we want to find 5 numbers between 1 and 2. There's a simple trick. We can just rewrite 1 and 2 as fractions. As you see here, we can use 6 as the denominator. So 1 becomes 6 over 6, and 2 becomes 12 over 6. And suddenly, boom, the numbers in between are obvious. 7/6, 8/6, and so on. The really mind-bending part is that you can do this forever. Between any two rational numbers you can find, there are infinitely more.
So let's recap. We have an infinite number of integers, and now we've found an infinite number of fractions between each of those integers. I mean, the line has to be completely full now. Our journey must be over, right?
Let's really think about this. The line looks totally packed. Our collection bag is overflowing with an unbelievable number of numbers. It feels like there couldn't possibly be any space left. But have we really picked up every single number?
And this is the most incredible, mind-blowing part of our whole journey. The answer is no. It's not full. Even with all those infinite fractions crammed in there are still infinitely many numbers left on the line, hiding in these tiny, microscopic gaps between all the rational numbers we just collected.
This discovery was so shocking that it basically threw all of ancient mathematics into a crisis. Way back around 400 BC, the Pythagoreans, the followers of the famous Greek mathematician Pythagoras, they were the first to stumble upon these mysterious numbers that just didn't fit their perfect worldview of numbers.
What they found were numbers that simply could not be written as a neat fraction of two integers. The legend, and it's a dramatic one, is that one of them, a guy named Hipparchus, was actually drowned by his fellow Pythagoreans for daring to reveal this dangerous secret to the rest of the world, the secret of numbers like the square root of 2.
So these bizarre new numbers were given a name: irrational numbers. Why? Because they couldn't be expressed as a ratio. They are the complete opposite of the rational numbers we just collected. You could almost think of them as the ghosts that live in the gaps on the number line.
So what do these numbers even look like? Well, you've actually met a bunch of them before. The square root of 2, the square root of 3, the famous pi, of course, and also any decimal that goes on forever without ever repeating a pattern, like that last example. They're all members of this strange, irrational family.
Okay, so we have our huge bag of rational numbers. And now we've discovered this whole other world of irrational numbers hiding in the gaps. Let's get to the final stage of our journey and see how this all fits together.
When we finally take all of those irrational numbers and add them to our bag that's already full of rational numbers, we've done it. We have finally captured everything. This complete collection, the whole shebang, is called the real numbers, and we use the symbol R. Now, every single point on the number line corresponds to a unique real number. The line is finally, truly full. Our journey is complete.
But you might be wondering, if you can't write these numbers as neat fractions, how do you even know where they are on the line? Well, we can actually pinpoint their location perfectly using a little geometry. Just look at this. If you draw a square where each side is exactly 1 unit long, the famous Pythagorean theorem tells us that its diagonal has a length of exactly the square root of 2. Then if you imagine taking that diagonal and swinging it down like a compass, where it lands on the number line, that is the precise, real location of the square root of 2. It has a physical place.
So, we did it! Our journey is complete. We've mapped the entire landscape of the real number line, from the simple counting numbers all the way to those mysterious irrationals. They all live together. But this leaves us with one last really cool insight. If someone just shows you a number written as a decimal, how can you tell which family it belongs to? Well, the secret is all in the pattern. If the decimal either stops or it falls into a repeating pattern, you know it's a rational number. But if that decimal goes on forever with no repeating pattern, then you know you've found one of those ghosts in the gaps, an irrational number.